On August 6, 1945, the United States dropped the world's first atomic bomb over Hiroshima, Japan, and then 3 days later dropped another over Nagasaki. These bombs, named Little Boy and Fat Man, were nuclear fission bombs that were based in uranium and plutonium isotopes respectively. If they were based in nuclear fusion technology, the impact would have been 1,000 times worse. This is TLDR Science, and today we're going to be talking about nuclear fusion. Fission power has been around for a while. You take heavy isotopes and collide them with a neutron to create lighter but still heavy products. Fusion, on the other hand, takes lighter isotopes like hydrogen and helium and collides them together to create heavier isotopes. In my previous video, we discussed how fission is more efficient than other sources of energy. But if you look at this graph, you can see how much more efficient fusion is at producing energy compared to fission. Fusion, unlike solar or wind, can run 24/7, regardless of sun or weather, and produces no radioactive or natural gas products. But what is the state of fusion, and when can we expect it by? Here's a quick rundown of where we're at right now. There are many different reactions that can be used for fusion, but the one we're most likely going to use is that between deuterium and tritium. This is because this reaction most easily overcomes Coulombic repulsion forces. This process produces an energetic neutron and a less energetic helium nucleus. So where exactly are we going to get these reactants from? Deuterium is commonly found in seawater and can be extracted easily. But tritium, on the other hand, is not only super expensive and hard to produce, but it's also incredibly radioactive. Not to mention, our current capacity for production is only 1 kilogram per year, and we're going to need something like 50 kilograms for fusion. We'll discuss this issue of tritium production later, but let's talk about the device we're going to use for fusion. It's called the Tokamak, and it heats hydrogen to 150 million degrees until it's a plasma, and all its electrons separate from the nucleus. The Tokamak then uses electromagnets to confine the hydrogen plasma into a toroidal or donut-like shape. The Tokamak has 3 magnetic components that create their own fields, and just like waves of water colliding to create an interference pattern, the magnetic fields interact with each other and create hotspots where plasma accumulates. This field structure can then be manipulated to keep the extremely hot plasma away from the walls of the Tokamak. To be clear, we have already achieved hydrogen fusion, but the issue now is doing so sustainably. We can measure how efficient a reactor is by looking at its Q value, which is just a ratio of its output to its input energy. Currently, it's around 0.6, which means that it's taking in more energy than it's outputting. A value of 1 would be a break-even point, where it's producing the exact same amount of energy as it's taking in. But for it to be economically viable, we're going to have to reach Q values of around 10. Back to the issue of tritium availability. You can actually line the insides of the reactor with lithium, and then the energetic neutrons produced in the reaction can collide with the lithium to create tritium. But this probably won't be enough to sustain the reaction. Finally, how exactly do we take any energy away from this? Well, we'd probably use tubes filled with helium that take heat away from the reactor and power turbines. There is a reactor currently under development called ITER, and it will be able to do fusion reactions by 2025. But it's only going to be able to do so sustainably by 2050, around the same time where we should be able to see fusion get on the electric grid. But that probably isn't going to be quick enough for climate change, which means for now, fission is probably our best bet. Thanks for watching.